Alright guys, so today what we're going to do is we're going to return to a problem that we've studied before, which is how to approximate the slope of a tangent line, this red line here, to the curve y equals x squared at the point 2, 4, using the slope of the secant line that connects the 2 points A and B. But we're going to do just a little bit of a twist to what we've been doing, so that instead of just approximating the slope of the tangent line, we're going to get the exact value. Before we dive into the analytical method, I want to make sure that everybody understands graphically what's going on. So remember, the method for approximation relies on moving this point B closer and closer and closer down along the parabola, and the closer the point B is to the point A, the more accurate our approximation is going to be. So a way to say this using a limit statement is that as the point B approaches the point A, the slope of the secant line, so the slope of the secant line approaches the slope of the tangent line. So as we move B closer and closer to A, the slope of the secant line will move closer and closer to the slope of the tangent line. Alright, so the analytical method, here it comes. So we used to define A and B as two different points. For example, A could be 2, 4, and B could be 3, 9, and then we'd move B closer and closer and use those 2 points to calculate slopes. This time we're going to do something a little different. We're going to define B not as a concrete number, or not as two concrete numbers, but we're going to define it using variables. So our x coordinate will just be x, and our y coordinate will be x squared. Why can we do that? Well, remember the formula is y equals x squared, so if we take that y value and put it in, our y coordinate will always be x squared along this parabola. But an interesting thing happens when we plug these 2 points, A and B, into our slope formula now. So let's take our slope formula and plug into it here. So I have m equals y2, and our y2 now is x squared. And then our y1 is going to be 4, so x squared minus 4. And then if we do the same, plug in our x2 value, which in this case is x, and then our x1 value 2, we're left with this interesting looking function that describes the slope of the tangent line. Why is this such an interesting function? Well, take a look. It looks very similar to some of the problems that we've been doing with limits. So we have a rational function where if we factor the top, the numerator, we get x minus 2 times x plus 2. And then if we leave the denominator alone, it's minus 2. We end up with factors canceling, and we're left with this equation here that the slope of the tangent line equals x plus 2. Why is that so neat? Well, remember what we said in the visual approach. We said that as the point B approaches A, the slope of the secant line approaches the slope of the tangent line. If I put these markers here to show that the x-coordinate here is 2 and the x-coordinate of B is equal to x, then I can kind of change my limit statement and say as x approaches 2, so I'll write this here, as x approaches 2, the slope of the secant line approaches the slope of the tangent line. A quick recap before we move on, just to make sure everyone's on board. So we started by saying as B moves closer and closer to A, the slope of the secant line moves closer and closer to the slope of the tangent line. Then we said, hey, another way to move B closer and closer to A is to take the x-coordinate of the second point and make it approach 2. So if I make this x move closer and closer to 2, that'll make B move closer and closer to A. Then we rewrote our original statement there. I know this is a lot of arrows, but let me just put a box around this so it's absolutely clear which one I'm referring to. As x approaches 2, so as we move that x value closer and closer to 2, the slope of the secant line will approach the slope of the tangent line. So now I'm going to rewrite this slope problem here. I'm just going to add this. This is going to be the slope of the tangent line as x approaches 2. So we can find the limit as x approaches 2 for this equation here. Then we'd have the slope of the tangent line. You might want to re-watch that once or twice just to see if you're on board with the reasoning. But anyway, this whole slope of the tangent line just becomes a limit problem. So if we scoot x closer and closer to 2, it's not good enough if it's 3. If we plug 3 into here, we'll get an approximation of the tangent line. But we want to see what happens when b lies right on top of a, and in order to do that, we need to find the limit as x approaches 2. And what is the limit going to be as x approaches 2? Well, we can't plug directly into our first equation, right? Because then we'd get 0 over 0, which is an indeterminate form. But luckily for us, these factors do cancel, the ones that are giving us the indeterminate form, and we're left with x plus 2, which is a function that agrees at all but one point to this function here. So now we can use direct substitution, and we plug in 2 for x and get 2 plus 2 equals 4. And what is this number here? Besides being the easiest math problem on earth, 2 plus 2 equals 4, this number 4 is the slope of the tangent line to the parabola y equals x squared at x equals 2. So this will be your problem for the video quiz tomorrow. I'll give you this equation, I'll give you this point, and instead of approximating the tangent line this time, I want you to use a generalized articulation of the second point, so x squared, and plug that, and then the particular articulation of the first point, a, 2, 4, and then x squared, and plug these 2 points into your slope formula, and then use a limit as x approaches 2 to simplify and get the exact value of the slope of the tangent line rather than an approximation, which is what we've been doing so far. Good luck.